In this video, we'll be looking at how to interpret SPSS output and how to write up the results. So just as a brief recap in terms of experimental variables, we normally have three types. So we can have things like constants. These are things that cannot be changed. So in certain analyses, you might have constant error terms, but normally these refer to constants within the physical world, such as the number pi or the speed of light. But as researchers, we care more about variables that we either control or want to measure. So these can be split into independent variables, which are stable variables that do not depend on other events. They are normally the things that we manipulate as researchers, such as group assignment or type of treatment somebody receives. While the dependent variable is something that will change and is variable as a result of other events. So for example, the participant's response due to what is happening. As a little illustration, you can imagine having two conditions where you either decide to water a plant a little or a lot, and the dependent variable in this case would be the growth of the plant, which you would hope is determinant on the amount of water or fertilizer that you decide to use. So I've tried to condense the important elements of hypothesis testing, and hopefully this will give you a rough understanding of the statistics we care about, why we report them, and why each one represents different information from our data. Statistical inferences are normally done on the basis of p-values. As a general definition, p-values should be seen as the probability of obtaining a result equal to or more extreme than what was actually observed in the data, assuming that the null hypothesis is true. One way of looking at this is how surprising is your data given the fact that you assumed there should be no effect or no relationship between multiple components. The way we normally make decisions about statistical significance is based on first conducting a statistical test. Then we compare this to a predetermined value, which we call the alpha. Typically, this is 0.05, but it doesn't have to be. This is an arbitrary number that we decide upon. We could use p0.1 or 0.001, which is what they use in other domains, such as the physical sciences, like mathematics and physics. Then we see if this p-value that we obtained when we compare it to this alpha that we determined, if it is less than the alpha, we say we can reject the null hypothesis. If it is greater than the alpha, we say we fail to reject the null hypothesis. So basically, we are saying that the data is not surprising enough for us to conclude that there might be a difference. Coming on to confidence intervals, well, these are kind of difficult to explain, especially since people always misrepresent them and misunderstand them. This is why I won't go into the way you should interpret them. All you should know is that they are important to report in your analyses for future reference. So you should understand that confidence intervals make statements of the probability of future confidence intervals. This is why they might not be relevant for your study currently, but they're important for the reproducibility of science in the future. So somebody in the future, when they're trying to conduct a similar study to your own, might care about what confidence intervals you obtained and then see what confidence intervals they obtained, and so on and so forth. And hopefully, based on the criteria by which we set it, we can have some sort of certainty about the estimates we are making about the population. You don't need to understand this very thoroughly. All you need to know is that they are important to report, and this is why I am stressing them in this video. Aside from p-values, what is also important to report are effect sizes, because p-values say nothing about the magnitude or the strength of an effect. Regardless of how small or large your p-value is, you cannot make any inferences about the size of the difference between two conditions or two variables you are testing. This can only be done by reporting effect sizes. Importantly, effect sizes can also be used to compare effects across studies. So because they are standardized measures, you can compare, let's say, the effect size, the Cohen's d of one study with another published study to see if there are differences, which one is larger, which one is smaller. In the absence of effect sizes, we cannot make any of these judgments. Now, finally, because these terms have popular understandings in terms of significance, importance, size, and magnitude, people fall into the trap of assuming they also mean practical importance. None of these, p-values, effect sizes, confidence intervals, none of them can express practical importance. So this is why we should care about a result or if it's important. This can only be determined through things like cost-benefit analysis, discussions on implications and feasibility, or other subjective considerations. You cannot make these on the basis of statistical inferences because you have no idea what may be important in a population versus what you consider is relevant. So simply finding something that is statistically significant, even if it has a large effect size, may not mean that it has any practical importance. When we run experiments, we are normally testing an alternative hypothesis, which is our beliefs as investigators about the real state of the world, compared to a null hypothesis, which assumes that there is no difference, there is no change, there is no relationship. This is important as some people confuse null with nil, but that is not the same. So the null hypothesis does not assume that a difference is of zero value. They just assume that the difference does not exist between two variables. So for example, if you're flipping a coin, the null hypothesis is a 50-50 split between heads or tails. It's not that the probability is zero. Alternative hypotheses themselves can be split into three forms. So these can be upper-tailed tests, lower-tailed, or two-tailed. The decision between these is normally made a priori, means before you start the experiment or you collect any of the data, and they are made on the basis of the investigator's belief. So you might believe that a specific intervention will lead to an increase in an effect. So this would be a tailed hypothesis, or you might simply be predicting that a change will occur between two specific conditions. So that will be the normal default two-tailed hypothesis. This is especially relevant in exploratory studies where you might not know or be able to anticipate the size and the direction of an effect. When conducting a one-tailed test, normally what you do is whatever the p-value from your test is, you simply divide it by 2, and this will give you a one-tailed p-value. However, what is important to note, and many people tend to overlook, is if the effect you find is in the opposite direction to what you predicted, so let's say you predicted a decrease, but you actually have an increase, you have to ignore this result. You have to report that it did not follow your expectations, and you do not make any inferences about what this might mean. And to understand why we care about things like p-values, especially 0.5, is because we care about the difference between type 1 and type 2 errors in our analyses and the way we conduct our research. So briefly, the alpha level, which is the probability that you normally set that you want to compare your test statistic to, is the probability of obtaining a significant result when in reality the null hypothesis is true. So this means that we set a value that we are comfortable with being wrong in the long run. So in this case, it might be 5%. So we are basically saying that we are comfortable with a 5% likelihood of being wrong in the long run with the type of test that we run, even if in reality an effect does exist between two conditions. Now, the beta value is normally the probability of obtaining a non-significant result when in fact the alternative is true. So this basically means failing to detect an effect or a change or a relationship. Normally this is set at around 20%, which is 1 minus the power of a study. So this is normally calculated as a with respect to your effect size and the number of participants you have. So we're basically saying that we are okay with failing to detect the effect that we care about 20% of the time. However, I want to stress that these refer to long-run frequencies, not per study frequency. In actuality, if you have no prior knowledge, you could basically say that your chance of being right or wrong is 50%, meaning that if you calculate the probabilities together, the reality of you finding an incorrect result is about 13%, not the 5% that people assume based on the p-value. So this is something that you need to be very careful with, and I recommend you study these tables to fully understand how errors are distributed and what type of inferences we're actually trying to make, as these can be very important, especially when it comes down to writing your conclusions about your study. So here I'm going to give you a template for the type of information you need to report when you conduct a correlation analysis, as well as examples of how the output should look like. When you conduct a correlation, be it Pearson's or Spearman's, what you need to report is should follow this specific formula. So you would have the R value, which represents, in this case, Pearson's R. You would put the number of participants within brackets. Then you would put the actual R value. So this would be the correlation coefficient, which for a correlation, you can also take as the effect size, so the strength of the relationship. Next, you would report the p-value, followed by the 95 confidence intervals for your difference, or in this case, for the correlation. So your output could basically fall into one of four categories. This is what the output would look like if you had a statistically significant positive correlation. So as you'll see, the correlation coefficient here is positive, as are the confidence intervals. If you had a negative correlation, you would see here by the negative value, and what you would get, instead of it being positive upwards, it would slope downwards. And you would see this again in the confidence intervals, as the bands between them would also be negative. The other option is, let's say you ran a one-tailed correlation analysis. So you basically predicted either an increase or a decrease. In this case, let's say I predicted that there would be a negative relationship. This is how you would report it. It would basically be the same as the other ones, but you would need to specify that it is a one-tailed correlation. Now, finally, if your correlation analysis proves to be statistically non-significant, this is what it would look like. You basically report exactly everything as before, but as you would see, the p-value exceeds your alpha level. If you wanted to plot a figure and report this in your results, this is the format that it would need to have. You need to clearly label your y-axis and your x-axis, along with the measure in which these values are coded. Alongside, ideally, if you can superimpose the R value and the line of best fit, this is also very good, and it's what is normal practice, so people just glancing at the figure understand what it is you are reporting. And when it comes to making inferences, you should rely on the metrics for effect size interpretation in terms of what is considered a small effect. So in this case, let's say the effect would seem to be a very large effect, while in this one that proved to be statistically not significant, but nonetheless, you would say that it's somewhere between a small and very small effect. However, it's important to not interpret statistically non-significant effects. And here's an example of how you would write up the findings of a correlation analysis in your papers. So you'd mention something like a Pearson's product moment correlation coefficient was computed to assess the relationship between, let's say, students' IQ score and their performance on an aptitude test. It's always good to remind your readers of what exactly your analysis was looking at without them having to search your entire paper. Then you would mention that preliminary analyses were first conducted to ensure that the data met the assumptions of a Pearson's correlation. The data was screened for outliers using visual inspection of box plots and calculations of standardized residuals using z-scores. And then you mentioned what your cutoff criteria was, because these may differ from study to study. You would say these did not reveal any data points which may be considered abnormal. There were also no missing values in the data set. With an equal number of observations in both categories. So you're basically trying to go over all of the assumptions of a correlation analysis that I mentioned in the previous video and demonstrating that you have checked for them and met them. Then you would say that the assumption of linearity was assessed visually using a scatter plot of the two variables, which indicated no violation. The normality assumption was tested using shapiro-wilks test, conducted for each variable separately, which did not reveal any violations of normality. And then you would basically report the shapiro-wilks for each of them separately. This was confirmed by investigating the histograms for each variable. Finally, the assumption of homoscedasticity was tested by plotting the standardized residuals against the dependent variable. This again indicated the variance are homogeneous between the two variables. So coming together, the fact that all of the assumptions of a Pearson's correlation were not violated, you can actually report the values that you receive. So in this case, you would say the Pearson's correlation revealed a weakly, or i.e. small, positive correlation between IQ scores and aptitude test, and you would report it in full as I showed on the previous slide. Alternatively, if some of the assumptions of Pearson's correlation were violated, you would have to report a Spearman's rank correlation instead. So much of the text in this case would follow exactly what you wrote before. You would still need to mention what the correlation analysis was regarding, and then you would mention all of the assumptions that you checked, highlighting the ones that in this case were violated. So for the experiment that I am reporting here, I can say that the assumption of normality, as assessed by the Shapiro-Wilks test, was violated, demonstrated that the assumption of normality is violated. And then I would report this and show that it had a p-value less than the critical alpha level by which I wanted to check. But it doesn't have to be the same for the other variable, but it is sufficient for normality to not hold. And then you would mention all of the other assumptions that you checked, you would report them in full, and then you would say, due to several assumptions of the Pearson correlation being violated, a Spearman's rank correlation was conducted instead. You would mention what you did with outliers if you detected some of them. In this write-up, I mentioned that I detected 2 data points that that I would consider to be outliers, but in this case, because Spearman's rank correlation is pretty robust to outliers, I decided to keep them. This is also important because people need to know how many data points you used to conduct your analyses. And then you simply report Spearman's instead of Pearson's. Moving over to the t-test, this is the format of your output and all of the values that you would need to report. So you would report the t-value and degrees of freedom for the test. You would report the t-statistic itself, the p-value that you obtained, and then you would need to calculate the Cohen's d. Unfortunately, SPSS does not do this automatically, and there is no easy way to do it. So what I recommend is follow this link and it will tell you what values it requires. It's just the means and standard deviations for your 2 samples, and it will give you a Cohen's d to report. Again, this is important to report in your inferential statistics, so people have an understanding that even if you found something that is statistically significant, how large is the effect between 2 conditions. Then you would report the confidence intervals and ideally the number of observations. So this is the total number of observations. So let's say if you had 2 groups, 30 and 30, you would say that the number of observations is 60. As a few examples, your output can either be in terms of you finding a statistically significant effect. So again, statistically significant, not just significant. That might be misconstrued. You may also report a one-tail test. So again, this is just the same as a two-tail test, the difference being that you would cut the p-value for it and you would need to mention it so people understand that is what you did. Or you might run into a statistically non-significant effect, in which case you would report it the same as the other ones, but without an effect size, because there is no point in trying to interpret an effect size for a relationship that does not exist. I've also given you here the interpretation value, so you know if the effect you find is very small, small, medium, or large. In terms of reporting an independent samples t-test, if it was statistically significant, I would recommend using a bar graph, and you should make sure that everything is labeled correctly and is clear to see. And you should also include error bars within your output, and if possible, superimpose any significance over the graph so people understand what it is that you found to be statistically significant. This is especially relevant if you would have, let's say, multiple conditions, and it would be difficult to interpret from a graph which were the differences that you found to be statistically significant. But in case you only have 2, this may not be relevant, but ideally you should get into the habit of reporting these as well. In terms of how you would write up the t-test, for a student's t-test, you would follow something similar to the correlation analysis, but providing a bit more detail. So in my fictitious study, I had 2 independent groups that were based on income. So these were low income individuals and high income individuals, and I wanted to measure them on levels of stress. So in this case, I would first report that the mean stress score of participants in the high condition was, and that would report the mean, standard deviation, and the number of observations that I had. So in this case, how many participants were in the high income condition, and that this was greater than the mean of the participants in the low income condition, which again, I would mention the mean, standard deviation, and n. So at this point, all I can say is that one appears to be bigger than the other one, but I cannot make any value judgments beyond this in terms of this difference meet statistical significance or not. So then I would report that before running a student's t-test, I conducted preliminary analyses to check for all of the assumptions that I mentioned in the previous video. So first I would look at the presence of outliers. So I would mention that I did this both visually using box plots and statistically using z-scores, and mentioning again my cutoff criteria. And I would mention if this report found anything that warranted attention or not. Next, I would check for normality, which can be assessed both visually using QQ plots and with a Shapiro-Wilks test. In this case, I say that I found no deviations from normality, and I report my Shapiro-Wilks. And lastly, I would look at the homogeneity of variance using Levine's test, which is automatically reported every time you conduct a t-test. So in this case, if I found it to be statistically non-significant, and you would need to report it basically the same way as you do an ANOVA, and this is how you calculate the degrees of freedom. So the first one is basically the number of groups minus 1. Since I had 2 groups, minus 1 is 1. And the second degree of freedom is calculated as the sample minus the number of groups. So in this case, if I had 60 and I had 2 groups, it comes out to 58. So you'd report this as well. And because all the assumptions that you have for the student's T are valid, you can report it in full, as I mentioned on the previous slide. If any of the assumptions of the student's t-test were violated, you would need to report a Welch's t-test. So in my fictitious case, I mentioned that through preliminary analyses, I found that the homogeneity of variance assumption was violated. So my data demonstrated heteroscedasticity, as shown by the Levine's t-test, which I would report in full. And as you can see, the p-value is less than the alpha criteria normally used. I'd also mention the other assumptions as well, so outlier analyses or normality investigations, and I would report these in full, and mention because I had an assumption be violated, student's T is no longer a reliable measure, I would use a more robust alternative. So in this case it will be Welch's T. So then you basically just report the statistics for Welch's T, which would just have it's the table underneath a student's T. You would have a different degree of freedom, which is corrected for the bias introduced into the data, but most of the other values are going to be exactly the same. Now I'm going to move over to SPSS and give an example of how you would conduct these analyses and the assumption tests, so you know where to find all of the values you need to report in your results. So now I'm going to briefly go over how you would conduct a Pearson's correlation, Spearman's rank correlation, student's t-test, and a Welch's t-test. First, I'm going to go over the assumptions that you would do in advance of running a Pearson's correlation, and then actually running it, and where you would find all the values you need to fully report your results. So as you see here, I've already set up a study where I have 40 individuals split based on gender. I recorded them on a change in percentage of confidence that they had after they received their marks, and then a change in marks the second time they took a test. So these are differences. This is why you might have negative, positive, or zero values. So they have an absolute zero only in the initial scale, and this one they could go from minus infinite to positive infinite. So all of them are interval style data. So the first thing you always have to do is simply inspect the data, see that you have all the cases filled in, there is no missing data, there is no apparent issues. Then you check the data type. So you'd go into variable view and you would check that, for example, gender is set as nominal. It has all the proper codes. Same for your two scalar variables. So everything looks in order. If there was any missing data or any sort of issues, this is where you would need to either try to correct them or at least report them in your analyses. Okay, so first, let's say we're trying to run a correlation between change in confidence and then change in marks. So the way you would do this is that you first have to say, I'm going to conduct a Pearson's correlation because I have two variables that are continuous. They have an equal number of observations, uh, and uh, and they're set to the proper type of data. So the first thing you would want to do is check for outliers. So the way you would do this is that you would conduct z-scores for both of these variables and see if there are any differences. Since in this case you would only be conducting a bivariate correlation, you don't need to split the data in any way in advance. So first we go to Analyze, Descriptive Statistics, and Descriptives. We put the two variables we care about in the variable box, and we click the box that says Save Standardized Values. After you do this, if you go back to your main window, you see that now you have two new variables that SPS has created. And what you would need to do is see if any of these values exceed your cutoff criteria. So in this case, is anything that has an absolute value higher than 3. So you can do this in multiple ways. If you want, you can just visually inspect it like this, but you can also right click and sort and see if there are any values that exceed your cutoff criteria. Same for this. So nope, at the moment, although some do seem to be a bit bigger, there is nothing that you should technically worry about. You can also investigate outliers using box plots. So the easiest way to do this is you go to Graphs, Chart Builder, and then you select box plots from here. So you basically click this, and then you select the single box plot that you want, and you put the scores that you are interested in on this side, and click OK. So this will bring up the box plot. And as you can see, the data looks roughly symmetric. So around the median, there are no deviations and there are no outliers indicated in the chart. I did the same for the percentage change in marks. And as you can see, although it's not as symmetric, there's nothing here that you would need to worry about. Next on the list is linearity. So you basically, because you're running a correlation analysis, it assumes that the relationship between these two variables would be linear if there is one. So the best way you can do this is you go to Graphs again, and you click this time Scatter Graph, and then you basically already have the marks here, and you put the confidence on the other axis, so you have your two variables, and you click OK. So as you can see, it seems to follow a straight line. It doesn't seem to have any S-shaped or upward curvature or anything that would not suggest linearity. One thing that I do recommend is double clicking the chart and then simply adding a line of best fit. They should also indicate linearity, so you should be fine with this assumption. The next step is to assess normality. So this is pretty straightforward. You go to Analyze, Descriptives, Explore. You add the two variables that you care about, and then you click Plots. You untick stem and leaf because nobody uses those. You click histograms and normality plots with tests. You simply click OK. It's going to take a while because this is a harder code to run. And then you basically have your case summary for the data. You can look into here to see the means and standard deviations. It will also show you, for example, the trim means differ significantly from the means, which may also indicate the potential existence of outliers. Skewness and kurtosis are mentioned here. This is relevant again to understand the distribution and the shape of your distribution. None of these seem to be higher than our cutoff criteria. And if we look at the test for normality, we see that the Shapiro-Wilks test for both of them is statistically non-significant. And this is also illustrated by looking at the histograms for the data. If you want to also add a normal distribution line, all you need to do is double click on the chart, and then it's this button over here. This would be a QQ plot. These are also very good to inspect. What you basically expect are that the points should basically match on the line and should not deviate either upwards or downwards too significantly. This looks okay. and you are also given again one of these box plots. You can look at the same for the marks. Seems kind of fine. Maybe it has a bit of skewness, but there was nothing in the output table that indicated this. Same with the QQ plot. Ideally, you'd have more data points, which would show a stronger trend, but this should be fine. And the same with the box plot. So now you can make the claim that normality holds because you've investigated not only the histograms, but you also had the Shapiro-Wilks test for the two variables. And finally, for the homogeneity of variance, what you need to do is conduct a linear regression. So you go to Analyze, Regression, Linear, and then you would basically need to select confidence would go into the dependent variable, but it doesn't really matter the order because it's the same as a correlation. You would click plots, and then you click this, which is the standardized residuals. You would put them on the y-axis, and the dependent would be on the x-axis. And that's it. You click continue, and you click OK. Gonna do its thing. It's basically gonna output the regression analysis. You can ignore most of it for now because all we care about is this. You can double click, add a line of best fit. So basically what we're looking for is that the points the points with respect to this line don't deviate too far. So for example, this might be a slight problematic point, but realistically most of them seem to be spread kind of equidistantly from this line. There are no huge deviations, otherwise the scale of this would have been completely off, where you would have a point over here where it might fan out, it might have different shapes, but if most of the points kind of seem scattered and equidistant to the line, then you can assume that the homogeneity of variance assumption is holds. And now that we've tested all of the assumptions, and currently all of them hold for my particular data, what you simply do is go to Analyze, Correlate, Bivariate Correlation. You would move the two variables you care about into your variable box. You can click on Bootstrap, click Perform Bootstrap, and then you click Bias Corrected Accelerated Percentiles. These are, accelerated intervals. These are the ones that are the ones you would want to report. And then I would recommend you also click Spearman's, so you can conduct both Pearson's correlation and Spearman's at the same time. If any of the assumptions that we just looked at would have been violated, you would have just clicked Spearman's and unclicked Pearson's, and that's how you would have done the Spearman's rank correlation. That is the only difference that you have between the two of them in terms of where you go to conduct them. You click OK, and the output should come out. It's going to take a while because it's running the bootstrap procedure. So you can look at the output. It starts here. This is the Pearson's correlation. As you see, the two are identical. They're just in the opposite direction. So you look at the Pearson's correlation coefficient. In this case, there seems to be a strong negative correlation between marks and confidence. And this is where you would have your confidence intervals that you would want to report alongside the correlation coefficient and the n number of observations that you had. If any of the assumptions had been violated, you would scroll down and you would go to the non-parametric correlation, where you would simply be reporting the values that you get from Spearman's rho instead of Pearson's correlation. Now let's assume that I wanted to also compare if there are differences in confidence change between the two groups of males and females. So I might be interested if in the change of confidence as a result of my marks is consistent across gender, or if there are any statistically significant differences between the two. So again, what we would need to do is the same as we just did for the correlation analysis, where we first decide on the type of test that we want. So in this case, we will want the student's t-test because we only have two independent groups with equal observations that are measured on a continuous scale. So we have to go through all of the assumptions of student's t to make sure that we can use it. And if we cannot, then we have to choose an alternative statistic. As with the correlation analysis, you would look at the data initially to make sure that you don't have any errors or issues. As we just saw before, the data is coded properly, there are no missing values, and we've also checked in advance to see if there are any outliers, and we didn't find anything that was worth noting, so we can just assume that there are no outliers in the data. There are two independent groups, and all of our values have paired responses. Excuse me, in this case, I mean paired in terms of that there are equal number of male and female respondents in the gender category. So if I try to arrange this and see if it lets me, you could see that I have 20 females and 20 males. So this is what I mean by equal observations. As before, we will need to check initially for normality assumption to make sure that our data is normally distributed. The only difference in this case is that because we have a grouping variable, we first have to split the data based on the grouping variables. The way you would do this is you go to data, split file, compare output based on categories, and then you pick gender. That's it. It understood that it needed to split the data file, and now you would look at the normality plots as we did before. So to do this, we just go to Analyze Descriptives, Explore Data. We add the variable we want to investigate. We would click on Plots, unclick Stem, put Histogram, Normality Plots with Tests, and click OK. Now looking at the output, first it's going to be based on the female category. So in this one, we see that we have 100% valid cases, no missing data. If we look at skewness and kurtosis, we also don't have any strong issues. Looking at the histogram, it does seem to have some skewness, but this is because of the limited data. But superimposing a normal curve shows that while the tail distribution on this end is short, it seems to follow a pretty normal distribution overall. Same with the QQ plot. There are some deviations. This is again why it's very good to have a larger sample size than just 20 participants. Box plot the same, shows kind of symmetric. There are no outliers visible, and there will be nothing that I would be too worried about based on the way it looks. Then we move over to the male category. Again, skewness and kurtosis are within bounds. The normality plot for this one does not look as normal as the other one, so there might be issues, but we will see in terms of the actual tests if that is a problem. So looking at the normality test for females, the Shapiro-Wilks is not statistically significant, so this does follow a normal distribution. And if we scroll down to the males, we will see that the normality test has been violated. So in this case, this is statistically significant, and this does not follow a normal distribution as would be indicated by the Shapiro-Wilks test, meaning that conducting a student's t-test on this type of data may not be optimal. Realistically, student's t is pretty robust even towards small deviations of normality, but for the sake of our analysis, it's always best to report Welch's t. In terms of testing the homogeneity of variance, this will be done automatically when we actually conduct the independent samples t-test. When you go to Analyze and then you go to Compare Means, independent samples t-test, and then we already have the grouping variable. I'm just going to reset this so you have an idea about what you have to do. Oh, initially I have to go and undo the split file because otherwise it will be splitting my data twice, which will not be possible. It will give me an error, but just to anticipate that, you take off the split file so it confirms that it's done it. Then you go to Analyze, Compare Means, Independent Samples t-test. You put the gender in the grouping variable, and you need to define the values you want. And then you would move over your variable. You click on Bootstraps, Bias Corrected. For the options, you don't need to click anything. Everything is fine, and the confidence level is what you want. And you simply click OK. It's going to run. It's going to take a while. And then you basically have some summary statistics about your data. So this is the means and standard deviation for your two conditions that you would need to report in your analysis. followed by the independent samples t-test. So in terms of homogeneity of variance, Levine's test says that everything is fine, it's not statistically significant, so we could assume the equal variance assumption and report a student's t-test. However, because we just saw that the normality assumption for males did not hold, it is recommended that we would report Welch's t-test, which is just the equal variance not assumed version. So you would report this t-value, these degrees of freedom, this significance level, and these confidence intervals for your data. And in essence, that is the only difference between the student's t-test and Welch's test within SPSS, is the difference between reporting the first row or the second row of your data, although statisticians are now mentioning that Welch's test is probably the better option to report under all scenarios, especially when you might have dubious assumptions that you are not quite certain if they are met or not. It's always safer to just report a Welch's t-test. And that should be it. That should give you an idea about how you should be conducting independent samples t-test and Pearson's correlations on your data, as well as checking for all the assumptions underlying your tests.